Hello everyone, I'm Mighty, your hands-on practice assistant. In this session, we'll go through a structural simulation together step by step and follow along with the practice example. In this example, we will perform a linear static analysis of a bracket. Linear static analysis is the most fundamental structural analysis method. It calculates deformation and stress under applied loads. The purpose of this video is to understand the overall workflow of structural analysis rather than advanced features. Let's briefly review the purpose of each step using the diagram on the screen. First, in the CAD model import step, geometry data is imported into NFX to create the analysis model. Next, define the material properties of the structure. For linear static analysis, Young's modulus and Poisson's ratio are required. Material density is also required when mass effects such as self-weight are considered. In the property and mesh generation step, material properties are assigned to the geometry. A mesh is then generated for the analysis. In the boundary condition step, define how the structure is constrained in the real environment. For example, bolted or welded connections can be represented using simplified constraints. Next, define the loads applied to the structure. Linear static analysis supports various load types such as self-weight, gravity, concentrated loads, pressure, displacement, and moment loads. In the analysis case setup step, select the type of analysis to perform. In this tutorial, we will use linear static analysis, the most basic structural analysis method. Finally, review the results such as displacement, stress, strain, and safety factor to evaluate the structural behavior. In this example, the bracket holes are fully constrained and a vertical load is applied to evaluate the structure. Before running the analysis, material properties, boundary conditions, and load conditions must be prepared. Now, let's begin the tutorial. First, click the New button in the upper left corner to open a new project. Then verify the unit system and click OK. Now, let's import the model. Click Import in the Geometry tab, select the example model, and click Open. Once the model is loaded, right-click in the workspace and select Hide All Guides. Next, let's define the material and property settings. Right-click Materials and create an isotropic material. Enter the material properties as shown on the screen. Move to the Properties tab, create a 3D property and assign the material. Next, let's generate the mesh. Click 3D in the Mesh tab to open the Mesh Generation tool. Select the model geometry and enter the desired element size. Click the More button and verify that the High Order Element option is enabled. Click OK to generate the mesh. Now, let's define the boundary conditions. Click Constraint in the Structural Static Analysis tab to open the function. Set the object type to face. Apply a fixed condition and click OK. Next, let's create the load condition. In the Structural Static Load tab, click Load and then click Constant Load to open the function. Set the object type to face. Select the loading surface of the bracket and add a force load. The load direction is -y. The magnitude is 1,000 newtons. This condition represents a simplified bolted connection of the bracket. To display the load value on the screen, enable Show Value in the Load Boundary options. All conditions are now defined. Let's proceed to the analysis setup. In the Analysis and Results tree, right-click Analysis Case and create a linear static analysis. Click Edit to open the Analysis Settings window. The left panel shows the defined conditions, and the right panel shows the conditions used for the analysis. Right-click the analysis case and select Run Analysis. Then choose a save location to start the analysis. The analysis is complete. Let's review the results. First, Double-click displacement in the analysis and results tree. Then review the overall deformation shape of the bracket. Click play to view the structural behavior animation. Autoscale exaggerates the deformation for easier visualization. To view the actual deformation, switch to real scale. Next, let's review the equivalent stress result. Equivalent stress represents the overall stress level within the structure. Enable the max and min value display option to identify the peak stress location and value. Finally, let's review the safety factor result. The safety factor compares the current stress to the material tensile strength. A safety factor greater than 1 is generally considered safe. The safety factor is below 1 in this case. This indicates that structural reinforcement is required. How was today's lecture? Simulation may seem difficult at first, but if you follow the steps and practice hands-on, you can get started with confidence. With MIDAS NFX, learn the fundamentals one step at a time and challenge yourself with a variety of simulation examples. Then, see you again in the next video. This has been Mighty, your hands-on practice assistant.